Hi, Monica. Today, our mock system design topic is design a distributed job scheduler like Airflow. The name Airflow could be frightening. It is not a everyday software that people use. But the idea is not complicated. It's, for example, you want to schedule an email to 100 people every day. You don't want to do that manually. So you could schedule a task. And the task is sending a message to 100 designated email address every single day on some time. That's the idea of job scheduler. And let's get started. First, let's start with the non-functional requirement. As the functional requirement says, users can schedule jobs to be executed immediately or at a future date. So the first, and they can monitor the status of the jobs. The system must be scalable to support up to 10K jobs per second. As always, as most of the tasks, we value availability more than consistency for this task. And as the functional requirement indicates, we must guarantee every task to be executed at least once. And with status returned to the user. The next one, the job scheduler, should be scalable. Scalable to support up to 10K per second. The core entities of the system includes, first, users. They are the people who schedule the task. And the second, jobs, like jobs are like I define a requirement. Send an email every 5 minutes or other frequency. That's jobs, job definition. The third one, this one is a little abstract, but also understandable. A job is a task to be run with a certain frequency and certain time. And the task is sending the email. So we have three entities: users, jobs, and tasks. API routes. I would provide 2 APIs to my users. The first one is to create jobs. It will need a HTTP post action to the endpoint jobs. The user should include the job definition, the frequency, and any parameters to execute the task. In our email example, that would be email address, receiver addresses, and email content. It would be a user-defined object. And the user authentication will be included in the header. We return the created job to the user as the response. The second API is getJob. User can get all the jobs or a specific job. They can request jobs within certain within certain time period, or all the jobs, or a specific job ID. And the same as the first API, user authentication is included in the header. We return job or jobs to the user. How will the jobs be scheduled and executed? To schedule jobs and executed jobs, it starts with users interact with the system client. The client could be browser or mobile applications. The user interacts with the client application, and then the client create job API. The client uses create job API. It sends the request to a scheduler service. The service persists the job definition into a database. The database could be SQL or non-SQL. For now, I would use DynamoDB. It can be changed based on further requirements. If the job table should include a job ID, user ID, that's the authentication the service grabs from the request header, and frequency, other parameters. We could include more in the future. For now, those are enough. To execute the job, I would have a executor. The executor should query the database periodically. We can define the frequency based on our requirement. It's a trade-off of efficiency and computation power. When every scanning of the jobs table, the executor creates a new table, and that's a tasks to be executed table. From the jobs table, it calculates for this scanning period the time bucket, this scanning time bucket, and the task ID I created. Then next task ID and next execution timestamp. That's the exact timestamp to execute a task. And of course, I should copy parameters to execute the task. And after executing, the executor returns status back to the execution table. After creating the table, users must want to see the status of their table and the tasks executed. They will still interact with the client, and the client sends a get jobs request to the scheduler service. The scheduler service validating the user's authentication from the header fetches related jobs and tasks from the job database. Fetches job status. Because there might be a long list of jobs to be executed or scheduled, the scheduler would also provide pagination back to when it returns jobs to the client to reduce the single trip's load time. How to ensure every job to be executed within 2 seconds of their scheduled time. Our current design couldn't guarantee every job to be executed within 2 seconds, because if we ask the executor scan all the jobs every 2 seconds, first the scheduler may not finish all the scanning. Second, it's a huge read load for the table. Because of that, I would update my design. I would add a message queue. To be specific, I would use AWS SQS specific queue type called delay queue, which guarantee the message, which is the task in our contact, become visible at an exactly defined time. That's the core, or that's the guarantee, that's the mechanism to guarantee the jobs to be visible within 2 seconds. And in this way, it doesn't matter that how often the executor scans the table, it transfers the reading load to the delay queue, which automatically handles the visibility of the message. Like even, for example, the executor read a huge amount of a message or task in this case, and the time bucket is a big bucket. But the delay queue would guarantee the message become visible to its downstream executor to execute. Because I add a delay queue, I would need another worker. So the executor basically become a task scanner. The task scanner queries jobs periodically and send the tasks to a queue. And that queue guarantees the visibility of the message. The worker pull tasks to execute. The worker always pulling, but the delay queue would only make the tasks to be executed visible to the queue. In this way, we guarantee the system execute jobs within 2 seconds of their scheduled time. I miss a case. There are another case is a user defines a job to be executed immediately. He or they don't want to wait. In that case, we need another mechanism. If the task is to be executed immediately, besides creating it in the database, the scheduler service should immediately insert the task to the queue. If the task is defined to be executed within 2 seconds, the scheduler should directly put the task into the queue. How can we scale job execution to support up to 10K concurrently? A common mechanism to support 10K level concurrent and executing in parallel is to use autoscaler group. There are many providers. I would use ECS, that's Amazon's AWS mechanism. It's called Elastic Container Service. What it does is it tracks certain signals or threshold. In this case, because we use AWS delay queue, the signals would be called approximate number of message, which is estimating how many message gonna be incoming. When the ECS detected that there are a lot of message waiting to be executed, it will automatically scale up the workers, which are the computing engine to do the task, such as sending emails. When it detects that the message incoming is coming down, it will automatically scale down. So that's that's how we support 10K level concurrent task. How should we handle retrying jobs that are fails during? There are two types of job failures. The first one is expected error. For example, the task is to send an email to some address, but some address not exist anymore, or network doesn't work at the time of sending. Those are application errors. For this type of errors, the workers can retry automatically with a defined delay time, because we don't want to retry immediately. That would cause traffic jam of retrying. So for application errors, retry automatically with exponential backoff. Retry limited with max retry count. Automatically with an exponential backoff means if is a common mechanism to delay more and more time with the retry counts increases. This time, the first retry I wait for 1 second, the next time I wait for 2, next time I wait for 4. That's the idea. Longer retries to make sure the system cool down, avoid traffic jam, etc. There's another type of error, that is, the worker crashes. If the worker crashes and it would not be able to send the signals whether the task is success or failed back to the queue. For that, I would use a mechanism which is an AWS feature called visibility timeout. It works in this way. The workers pull tasks and run it. When it's success, it will return the status back to the database and also delete the message from the queue. However, if the worker crashes, it would not be able to delete the message from the queue. And the queue, without saying the delete signal, it will make the message visible again. And when the message is visible again, other workers would pull it to execute. And that's how we solve the problem. We solve the error of worker failure. Oh, that's all.
That it?
That is. We finished.
Wow. Boy, that was really interesting. So let me show you what